Hello everybody, my name is Majid and this is a joint work with our collaborators Kim Hall and Joe Albers and my advisor Tom Dieterich. So first I would like to talk about the motivating application of my research I've been doing in the OSU, which is invasive species management river networks. So the type of invasive is a tree or plant. The name is tamarisk. It's originally from Middle East. Has been invaded over 3 million acres of land in the western United States, and it basically grows by the river, by the water, and outcompetes with native vegetation for water, and it causes some problem for the environment. So the question we have here is, what's the best way to manage a spatially spreading organism? So, like many similar problems, you can formulate this kind of problem with Markov decision processes by using a tree structure of this river network. You can define state actions, and by adding dynamics, you can basically we can basically answer the previous question by minimizing the expected discounted cost of invasion, and cost of management subject to some budget constraint. So the code for this simulator is available if anybody is interested to use, and it would be nice for the community if we have like shared data and also shared code repository for the code. So let's talk about the research I have been doing. So another motivation, as Sean mentioned, is some of this ecosystem management simulators expensive. Expensive in terms of taking samples. It takes a lot of time to get next sample. So I am focused on basically pack MDP planning. I want to find a policy which is near optimal with high probability, while I want to minimize the number of simulator calls I'm taking. In other words, I want to have the guarantee on the policy I'm going to compute and output to the stakeholders. So first, we started, if you want to be efficient about samples, you have to allocate them efficiently. So we started by allocating the sample efficiently for policy evaluation first, then we extended to policy optimization, which is mainly our goal for this research. So you can see here that we we allocated a set of we come up with a set of algorithms for each competence interval and set of benchmarks for tamarisk domain on the right-hand side and some other benchmark domains. And you can see that on vertical lines, we basically calculate what is the uncertainty in the starting state after taking that many samples. And the lesson from this policy evaluation is trajectory-wise empirical bench time bound is the best algorithm you can use. We try to extend the idea we had for policy evaluation to policy optimization, and here we can see we propose a local global confidence value algorithm, which DDV is another our previous algorithm, which you can see on the left-hand side. On some of the other benchmark, they are comparatively the same, but on Tamarisk benchmark, it's much better. It's doing much better than DDV. And Fichter algorithm is one of these algorithm in the literature. And at the last, I want to talk about this. My last slide. I want to talk about my ongoing project, my ongoing research, which is now I want to extend pack optimal planning to pack safe optimal planning. Give you an example. We are basically considering the risk as a probability of entering to some catastrophic state. For example, some catastrophic would be some extinction risk. So I guess that's my talk, and thank you.